Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I appreciate you joining me here today for what I think is a very exciting episode of Nunley Math. It's exciting to me because this is the first in our series of videos on pre-algebra. You'll remember that last year we spent our entire time together talking about Algebra 1, and I mentioned to you that I create these specifically for the students in my class, but that I hope you can get some benefit and some value out of them as well. My plan this year is to try and do as much as I can for my pre-algebra class or my 7th grade advanced students. And once again, I hope that some of you will come along with us on this journey. The nice thing about a pre-algebra class is we get to talk about a lot of different things. We get to do a little bit of algebra, a little bit of numbers, a little bit of geometry, a little bit of probability. So a little more variety in terms of what we get to talk about. I always like to start my year off talking about numbers and number systems. Numbers and number systems. It's kind of fallen out of fashion to talk about numbers and number systems in a junior high setting because there are a lot of definitions involved. But what I've found is that when we get to Algebra 1 and we begin talking about domains and ranges and what numbers make sense, that knowing a little bit about number systems is very helpful to us. So we spend a few days talking about number systems and then we use it to guide some of our discussion about how to deal with fractions and decimals and square roots a little bit later on. So without further ado, let's work our way through this. If I ask you to think about all the numbers that were between 1 and 10, that's inclusive, meaning including 1 and 10, could you provide me with a list of those numbers? Now, most of you would probably say, yes, that's very, very easy, and you would probably say to me 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. But if I prodded you a little further and said, are there other numbers that are between 1 and 10? After a few seconds of thought, you'd probably come up with a lot of different answers. Like maybe you thought of, 3.2? Well, that's between 1 and 10. 9.1? How about the fraction 3/4? Or a lot of you might be familiar with the mathematical constant pi, 3.14, on and on and on. Or radical 15. Oh, here's one for you, 6.2 repeating. Or 6.12345, 6, and on and on. You see, when we talk about numbers between 1 and 10, most of us have been conditioned to simply refer to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 without thinking about the fractions and decimals. And that's really more of a reaction than a fact that we don't understand what's going on between 1 and 10. But I mentioned that on purpose because the answer to this question and to a lot of mathematical questions depends a great deal on what number system we're working in. The set of included or allowable numbers is often referred to in Algebra 1 as the domain. Here again, the word domain is not overly significant for us at this point, but I do want you to be familiar with it because it does come up quite a bit in the future. Now, I'm going to spend the next couple minutes introducing you to several of these most common or most commonly used number systems. There are a lot of different number systems. For example, if I said to you a number system is a group of numbers that all have a mathematical characteristic or quality in common, and I gave you the idea of evens, you could probably generate for me many different number systems. You might automatically think of odds or primes. When I mention primes, people usually come back and mention composites. We have a set of numbers called triangular numbers. We have multiples of 7, we have the perfect squares, and we have complex numbers. Lots of different ways to group or think about the numbers, but there are some groups that occur more frequently or that are more useful to us than others. Here are the 7 number systems that we commonly use in pre-algebra mathematics. Counting numbers or natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers, and then occasionally we refer to imaginary numbers. And we'll talk about each of these in more detail as we go on. I'm going to work my way through these and just kind of give you a definition for each one of them, and then we're going to look at how they're related to one another. Now, It is very important for us when we're talking about numbers to think about what number system we're in. For example, if I were to say to you, I have half a candy bar, that makes perfect sense to us. But if I were to use that same number system, this same fraction 1/2 when referring to a puppy, now all of a sudden you've got a much more, is twisted the right word? A much more twisted or demented way of thinking about it. When we think of puppies, we don't usually think about fractions or decimals, but certainly we can think about having fractions of candy bars. Again, knowing which number system we're talking about helps us make sense of the kind of items that we are dealing with. Now, counting numbers or natural numbers are the first numbers we tend to teach to children. We learn them at a very, very young age. We call them natural numbers because they occur naturally in our everyday life, and most people can understand them without much of a description. So, when we think of counting numbers, we start off at 1 and we do 1, 2, 3, 4, 5, 6, 7, like we did in our original example a few minutes ago of when I asked you to do numbers from 1 to 10. In fact, I've got a quick little fun illustration for you. This is a YouTube video I grabbed from Sesame Street Workshop, actually, where we're talking to children about the numbers 1 through 10. As I skip right over that, let's try and click that again. There we go.
Greeting. I am the Count. Do you know what? Look, flowers. I will count them. One flower. Two flowers. Three flowers. Four flowers. Five flowers. Six flowers. Seven flowers. I love to count flowers. Do you know why I love to count flowers? Because flowers make me sneeze. And now, after I count the flowers, I can count sneezes. One sneeze. Two sneezes. Three sneezes. Four sneezes. Five sneezes. Six sneezes. Seven wonderful sneezes. I love it.
And there you have the count, teaching children how to count using flowers and sneezes. Again, I grabbed that video just off of Sesame Street, put it in the video for my students to enjoy, but it does illustrate a really good point, and that is this is typically where we start our understandings of number systems, counting or natural numbers. Now, as children tend to get a little older, we begin to introduce this idea of zero. How as soon as we introduce zero into the mix, we now have this set of whole numbers. In fact, the only difference between the whole numbers and the natural or counting numbers is the addition of this zero. In more complex math problems, there are some things that you can do with most numbers that you cannot do with zero, and so it's sometimes excluded, but it is important for us to be able to differentiate between the two. Next up, we tend to talk a little bit about integers. Integers are all of the whole numbers and their opposites. All the whole numbers and their opposites. So we can see over here on this thermometer, I have 0 degrees, I have 10 degrees above 0, 20, 30, 40, 50, and so on. But if I want to think about temperatures that are colder than 0, then I begin working in the opposite direction. I'm still 10 degrees different from 0, but I'm now 10 degrees below. If I have this 0-degree starting point, I can either have temperatures that are above that starting point or below. This idea of an integer allows us to differentiate between the two. The positive, of course, meaning higher than 0, the negative number, of course, meaning below 0. Notice that the positive values go up, 0 has no opposite, and negative values go down. It's also important to note that everything counts from 0, so notice that 10 spaces in one direction, 10 spaces in the other direction, 20 in one direction, 20 in the other, 30 in one direction, 30 in another. Not every negative number would be considered an integer. Remember, integers are just the whole numbers and their opposites. Because of that, we write it this way: 0, 1, 2, 3, 4, 5, 6, 7, on and on and on, and then the opposite of those, -1, -2, -3, -4, -5, on and on in the other direction. Notice that I did not put my ellipse in here. That's those 3 dots that tell us that it goes on and on, but I can certainly add those in real quick, just like that. We can talk about rational numbers. Rational numbers are any of those numbers that can be written as fractions. Now, I want you to think about that for just a second. Up until now, we've had whole numbers and their opposites, 0, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. But we can also begin to think about pieces of things. Pieces of things. Now, you should have done a lot with fractions when you were back in elementary school. It's important for us to remember there are a lot of things that can be written as fractions. For example, the whole number 5 could be written as the fraction 5 over 1 or 10 over 2. Mixed numbers like 3½ can be written as fraction. And every decimal that terminates can be written as a fraction. Remember, when I say 5.2, the appropriate way to read that is 5. We read the decimal as the word and then we read this giving its place value, 2, and it's in the tenths position. 5 and 2/10, of course, could then be written as the improper fraction, 52 over 10. Now this, of course, is not our focus for today, so I'm just going to briefly hit on that. We'll talk some more about fractions here in the near future. Also, we need to keep in mind that any decimals that repeat can also be written as fractions. 0.3 repeating can be written as 1/3. 0.5 repeating can be written as 5/9. And we'll actually take a couple days and we'll work on converting those back and forth, but that is not our focus here today. I just want us to recognize that any decimal that terminates or repeats can be written as a fraction. And since they can be written as a fraction, they would be considered to be rational numbers. Now, I did give a list of several examples here. Notice you've got just a fraction. A negative fraction would work as well. 0 would be considered a rational number. 5. Notice 7.21 over and over, or 9.5 repeating. All of those rational numbers. The irrational numbers are the ones that are going to be much less familiar to most of us. Irrational numbers are those that are not rational. That's what the prefix IR actually stands for. It means not. Let's see if I can get that right. There we go. Not rational. Not rational numbers. So basically, everything that can be written as a fraction is rational. Everything that cannot be written as a fraction is irrational. We don't talk about them a lot very early on in mathematics because they tend to be a little bit confusing and they're very, very hard to write. These are the numbers that are non-ending, non-repeating decimals. A square root that is not a perfect square would come out as a non-ending, non-repeating decimal and would be considered to be irrational as well. So if I wanted to give you an example of an irrational number, I'd have to do something weird like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on and on and on, where you can clearly see that there's a pattern here that will not repeat. Or I might give you some bizarre, obscure pattern like, let's put a decimal here, 17.265489, where you can't see any pattern. And I've got another one of those as well. Again, these are very hard to write. They're difficult to add and subtract, multiply and divide because they just keep going on and on and on. If you were to work with them, you would have to keep writing forever. It would be very challenging. The other thing that we could do, and most of the time we usually end up doing, is we usually round these off to the nearest rational number. So either the nearest tenth or the nearest hundredth, or here nearest thousandth, or whatever is most appropriate. Most of us would not deal with all the digits. There are a couple irrational numbers we are familiar with. Remember, pi is 3.14159, on and on and on. Most of the time in elementary school, we just deal with 3.14, again, using that rounding. And any square root that is not a perfect square is going to come out as an irrational number. This is going to be, I think, 1.4 something, something, something. There again, that's off the top of my head. Don't hold me to that. We'll talk some more about these as well over the course of the next several weeks. The important thing now is just to realize what exactly it is. These are pretty easy to spot because they tend to be just bizarre looking numbers. Makes them easy to pick out. Now, most irrational numbers will come from square roots that are not perfect squares, at least in my experience. The last thing I want to make sure I talk to you about is imaginary numbers. We don't really discuss imaginaries a whole lot in junior high math, but I will make mention of them. Basically, you can be assured that most of the numbers you know are real numbers, unless you're somebody who studied some advanced mathematics. Everything you can think of just about is a real number. In this unit, if I ask you, is it a real number? The answer is going to always be yes. The formal definition of a real number is actually something that can be found on a number line. Again, everything we can possibly think of at this point probably is a real number. I do talk about imaginary numbers just briefly. Short version is that they're numbers that can't be found on a number line. They don't really exist, but sometimes we pretend they do in order to make certain mathematical operations easier. Again, way farther down the road in Algebra 1 class, we talk a little bit about imaginary numbers, but not too much here. I can give an example of something that would be imaginary, something like the square root of -4. Square root of -4 is imaginary because there's nothing that times itself equals a -4. 2 times 2 is +4, and -2 times -2 is also +4. So there's no way for me to get the square root of a -4. There are some instances, though, where in higher mathematics we can pretend we know what this answer is because it's something that's going to get undone in a minute anyway. Again, way on farther down the road, not something you need to worry about, but if I don't talk about it, people ask me about it, and so we'll go ahead and just throw that out there for you. Now, those are our basic number systems. I've got two study tools for you that I think will help us as we begin to look at these number systems. Notice that each of these boxes represents one of those number systems, and the lines represent the relationships to one another. It's important for us to realize that we don't have natural numbers over here and whole numbers over here and integers over here. These aren't several distinct groups. Instead, it's an organization of numbers from groups that are very specific to groups that are very general. So when I look at this list up here, the real number system is anything that can be found on a number line, anything that I can find on a number line. If I have a real number, it will either be rational or it will be irrational. It has to be one or the other. Either it can be written as a fraction or it cannot be written as a fraction. Now, if it cannot be written as a fraction, then I basically am just going to call it an irrational number and be done with it. But if it can be written as a fraction, there are several other ways to break it down. Some of these rational numbers have distinct characteristics. For example, the integers, you'll remember, are all the whole numbers and their opposites, or they're all the numbers that don't have fractional or decimal parts. The whole numbers is a subgroup of that. This is just those numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on. And then the natural numbers is all of the whole numbers except the natural numbers do not include 0. You see, this is an organizational structure. You have things that are very specific down here, a very small group, that fits into the larger groups that are above it. So that if I tell you a number that's a whole number, like 7, If I know that 7's a whole number, 7 is automatically an integer, a rational number, and a real number. A 7 down here is automatically going to be everything else above it. Now, could it also be a natural number? Well, yes. In fact, it is a natural number. But when I see this list, if I can pick one of these categories out, I know that it must be everything above it, and it might be everything below it. It will never be both rational and irrational. Now, I recognize that's a lot of information all at once, but let me see if I can help you play with that just a little bit. Here's a number for you, and this looks about like what I would give for my students for homework, the number -15. Now, I know that my natural numbers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. This is not a natural number. In fact, well, I'll do it in a second. I also know that whole numbers are 0, 1, 2, 3, 4, 5, 6, 7. This is not a whole number. But it is the opposite of the whole number 15, so it is an integer. Not a counting number, not a whole number, but it is an integer. If it's an integer, that means it's automatically rational, which means it cannot be irrational, which automatically makes it a real number. I could use the name real, rational, or integer to describe this number. And I always want to describe it giving the most specific name, which means I'm going to refer to this as an integer. See how that works? That's an integer. Now, there is another way to do this, so I'm going to erase all these marks for just a second, erase all ink on the slide, and I'm going to walk through this again. What I did is I found the lowest group, and that told me automatically that it was everything above. I could also do it the other way around. I could walk through here and start at the top and say, okay, is it real? Well, basically everything we know is going to be real, so you're always going to circle real in this class. Then I have to choose, can it be written as a fraction? Or can it not be written as a fraction? Well, I know -15 can be written as -15/1, which means it's rational. If it's rational, it cannot be irrational. I go to integers. Remember, the integers are all the whole numbers and their opposites. -15 is the opposite of 15, so it would be an integer. Is it a whole number? No, it's not a whole number because whole numbers would not have negatives. The whole numbers would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if it's not a whole number, it cannot be a natural number. As I'm coming down this list, as soon as I mark off one of these, I know it won't be in any of the groups below because I'm starting from something that's very general and moving my way down to something that's very specific. Once I know the most specific name, I'm going to fill that in. There is another tool that we sometimes use that looks more like this. Some of my students prefer this because it's a little more visual. Notice that I have this big circle that includes all the real numbers or everything that we know. I then have my rationals and my irrationals. Notice I really should have done a dividing line down the middle and had all the rationals and irrationals because those are the only two options within the real number system. I shouldn't have all this blue space, but this is a very common graphic, so I went ahead and used it. Since I have the number 0, I'm going to start from general and work my way to specific this time. Also notice this does look a lot like the table that I showed you before. I'm going to go from general to specific. Is it real? Well, yeah, everything we can think of in this class is a real number. Is it rational or irrational? Can 0 be written as a fraction? Well, yeah, it can, which means it's rational, not irrational. The integers are all the whole numbers and their opposites. Well, 0 is a whole number. Since 0 is a whole number, I circle it. But it is not a counting or natural number because counting and natural numbers start at 1. That means the best name I can give to this is a whole number. See how all that fits together? It can be a little tricky. That's why I do have the two graphics. I personally am a fan of this one here, but again, a lot of my students tend to like this one over here. I would recommend taking screenshots of these two graphics and printing them off for yourself if you don't already have a copy. I think they'll help you as we work our way along. What I am going to do is I am going to give you 3 examples. What I'd like you to do is try these on your own, and then I'm going to go through them and talk about how I rationalize my way through them, and then we'll let you check and see how you did. I'd recommend pausing the video because I am going to keep going so I don't have a lot of dead time in the video. When I look at -8, everything I know in this class is going to be a real number. I can find a -8 on a number line. Can -8 be written as a fraction? Well, sure it can. That means it's rational, not irrational. Remember, I always choose between those two. Is it a positive or is it a whole number or its opposite? Well, yeah, it's a negative or opposite of 8. 8 is a whole number. 8 is a whole number, but -8 is not. That means it's not a natural or counting number. It is an integer. And I don't know why that didn't mark out. I have to go back and fix that. There it is. Okay. How about 3/5? Well, it is real. Everything in this class is going to be real because we don't deal with imaginary numbers. I have to decide, can it be written as a fraction or not? 3/5 is a fraction, so I know it's rational. It can't be irrational. Is it an integer? Well, integers are all the whole numbers and their opposites. This is not a whole number. It's also not the opposite of a whole number, which means none of these other names will apply, making it rational. Last one, square root of 15 is a real number. It's actually going to be on a number line. It's slightly less than square root of 16, which is 4. Again, we'll deal a lot with square roots in the coming weeks, just not yet. Every square root that's not a perfect square is going to be an irrational number. Remember from our first graphic, if it is irrational, it is not going to be any of these other things. And there is your solution. Couple last minute things real quick. If I ask you why is something a particular number system or prove that it is a particular number system, these are the definitions that I would expect my students to use. It's real if it can be found on a number line. It's rational if it can be written as a fraction. It's irrational if it cannot be written as a fraction. It's an integer if it does not have a fractional or decimal part. Whole numbers are the non-negative integers. You could also say the counting numbers plus 0. And then for counting or natural numbers, I would say the positive integers by themselves. Notice the difference between the word positive and non-negative. Last thing I would expect my students to be able to do is I would expect my students to be able to select a correct domain if I gave them a situation. So for example, I ask you the number of 2-liter bottles of your favorite soda at the grocery store. I would ask my students which number system would be appropriate or most appropriate. Would we say it's real? It can be found on a number line. An integer because it does not have a fractional or decimal part, or the whole numbers, which would be non-negative integers. Probably in this situation, we'd be looking at whole numbers. You don't really have negative bottles of soda, and you definitely don't want to see a fractional bottle of a soda at a grocery store. The difference between your estimated number of party guests and the actual number, I would say this is probably an integer. If I have more than my actual guests, or more guests than I predicted, I would have a positive integer. If I have fewer guests than I predicted, I would have a negative integer, but I certainly wouldn't have fractions or decimals of people arriving at my party. The number of cats at an animal rescue. Again, this is like the puppy problem we talked about earlier. Hopefully you're dealing with whole numbers. I know cats can sometimes be negative, but certainly that's a negative using a different connotation. You don't really have negative cats. The number of pretzels in a bag. I would probably call this real numbers. You can have fractions of pretzels. You can have half a pretzel or a third of a pretzel. Your pretzels can be broken into lots and lots of pieces, so probably real numbers is most appropriate. You don't really have negative pretzels, I wouldn't think. So if I want to get real specific and real confusing, I could say we would only be using positive real numbers or non-negative real numbers, but we're not going to demand that much of you at this point. How about the number of coins in your piggy bank? Probably whole numbers. You don't really have negative coins. You shouldn't really have fractions of coins either. Your distance from sea level. I would probably go with real numbers here. I can be above sea level or below sea level, so positives and negatives. I could also be fractions of miles or fractions of inches above sea level. The difference between the number of coins you have and the number your sister has, probably again integers. Since you're dealing with coins, you're not really talking about fractions or decimals, but since you're doing a comparison, you might have more than she has or less than she has, which means integers or positives and negatives are probably going to be useful to you. Again, thank you so much for taking the time to watch with us today. I'm real excited to start this new series with you. I know this first lesson is a little dry, there's a lot of definitions in here, but it's going to give us the ability and the power to do some really cool things in the coming weeks. So I hope you'll come back and watch again. Best wishes to you all. Make sure you smash that like button, subscribe so you can follow along with the stuff we're learning this year. Leave us a comment in the comment section. Let us know that this is helpful to you, or if it's not, maybe leave us some advice as to what we can do to make this better. Thanks again, you guys. Take care.